about is model calibration. Now, for the workshop, I've mentioned this several times, and we don't have time to calibrate. Calibrate usually takes weeks. Okay, so I'm going to explain the steps that you would do, and explain the process and the theory behind it. Okay. So, like I said, this is the last one. So after you would complete, you would normally do this step. So we said the steps in modeling, we had all those beginning steps. These are the last steps. Okay? Which is calibration, which means selecting parameter values that are within acceptable limits to fit the data to. So this is a key term, acceptable limit. Then we validate it, applying the same model and the calibrated parameters to an independent data set. So we talked about those two before. We would run a sensitivity analysis to assess the impacts of changes of uncertain values on the model outputs. So for example, can I see that piece of paper right there? Your data sets right now that we gave you can fill in the areas in the red, right? Okay. Well, every single parameter is a parameter that you can calibrate. Okay. So what I would do is, in one of these, for instance, this one down here says soil ALB. It's called surface soil albedo. It means the reflection of the surface. And we don't have a value. So we left it as a normal value. So I would run my sensitivity analysis. And you will find that this parameter is very low, meaning it's not sensitive. Meaning if I had 100 versus 1,000, I still have the same runoff. If one of the ones you are missing is a sensitive parameter, then you have to go back and somehow get that data. So here we used as best as we can, and if any of the ones that we do not have are sensitive, then we'll go back and get them somehow. Does that make sense?
Yeah.
And then the last thing is uncertainty analysis. And says assessing the range of model outcomes likely given uncertainty in parameters, model error, and exogenous factors like weather. So for example, what this is saying is I have a calibrated model or a observed value and calculated value, right? And we want to say what parameters can I change to make them match. We agree with this?
Mm-hmm.
That's calibration. Okay. Well, I told you there are 1,000 parameters. So it is possible that I can change 10 parameters and they match. It is also possible that I can change a different 10 parameters and match. Does this make sense? So meaning I can take, I'm going to go all the way back for a minute, just to make this clear. I can take these 5 or so, 6, and it will make my observed meet my calculated. I can take just these 5, and it will make the same graph. So which one is correct? So here I'm changing, I take 5 that deals with soil. This is hydraulic conductivity. This is the roughness, the soil depth. So these 5, when I change them, they give me a perfect match. Okay? But if I change the surface lag, available water content, and curve number, it also gives me a perfect match. So which one is correct?
Changing the parameters for which are not measured.
Oh, sure, but let's pretend all of these were measured. Okay? So how do you... So does that mean that changing this is correct? Or does that mean changing this is correct? So you don't know. But there are times that 2 things can give you the same result. And we call that uncertainty analysis. So when I go all the way back, that's what we're looking for. Are there a different set of values that will produce the same result? Because this is very important. If there is, then like Hen had stated, if there is a different set, then we would use the one that we have the most certainty for, the most field data for.
So which one of the two will we use to make to change to make matching? Which one of the groups? You have two groups. Which one of?
I gave that. That was an example. I wouldn't say it's group 1 or group 2. It would depend on which one you had more field data for.
So it will depend on if I have the first set have
all, and the second only has half. So what this will do is this program will run automatically. And it will tell me that there are 5 sets that give you the best result. And I would look at those 5 sets, and I would look for the ones that I have the most field data for, the most certainty for.
If all of them have field data,
then it doesn't matter. Yeah. But you will not have this.
If, for example, for uncertainty analysis, for example, I have 2 groups. It is possible, for example, to change, for example, the 5 with small change, and look the results, and after that make that, for example, 100 times, and after that make some analysis, statistical analysis, maybe principal component analysis to see if there is correlation between 2 parameters.
Yes.
And after that, can I determine the parameter that is most sensitive and that?
Yes, you could. But what you're describing is everything manually, when SWOT can do it automatically.
I can do that, this analysis.
Yes. And I will show them to you.
Okay.
Okay? So we said we have the calibration is simple. We take the computed and we match observed and see if they match. No problem. I mean, we all understand the idea behind it, right? So again, this happens to be groundwater head. Earlier today I showed you stream flow.
Oh.
Okay? So we said there's 2 ways to calibrate. 1 on stream flow, 2 on groundwater. In this case, groundwater head. Everyone knows what the term, I assume we call it the same.
Yeah. Head.
The water level, the head of the water. Head. Top. Okay? So now the second thing is, how do we evaluate that this is correct? And we do that using statistics. And we determine the quality, and most importantly, the reliability. How accurate, or how much can we rely on this model? And I mentioned the 2 methods before. The first one is coefficient of determination. Other one's called Nash-Sutcliffe. So I actually am starting with the second one first. So this is the measure. This is the paper if you want to see it. Nash-Sutcliffe efficiency measure. And that's what its equation is. I won't go through it. You can kind of go through it. And it's used to assess the predictive power. The most important thing I mentioned is, I'm going to draw this again. I'm going to draw this on the board. Okay? Which says that if I have that, okay, and I'll say this is 10, 20, 10, 20. So of course, if I have perfect data, it would be there, it would be here, and I would draw a line, right? Perfect. Now, if I have data points that for every 10, I get 1. For every 10, so what would my value be in the y? If I had a value of 20, what would 2? Right? So if I use the coefficient of determination, or r squared, it would give me a value of 1, meaning a perfect correlation. Because the correlation is every 10, I get 1. Every 10, I get 1. That's perfect.
Yeah.
It's just comparing it one data set to another. It's not looking at the value of the data set. It's looking at the degree of correlation. Does that make sense? So that's R squared. So instead, we use Nash-Sutcliffe. Nash-Sutcliffe compares it to a one-to-one line. So this, if your data looked like this, your result would be 0.2, very bad. The closer it is to this line, would be better. Does that make sense?
Yeah.
Close to the red one.
Yeah, closer to what we call a one-to-one line. So my point is if anybody shows you data and they say the R squared value, most of the time that means nothing. Does that make sense? I mean, it still has importance, but you could trick this number.
But most of people I see that they use coefficient of
I know.
determination.
And they're incorrect.
Maybe famous authors use the same
Sure.
R squared.
And those famous people are incorrect.
R squared is the coefficient it's also calculated in SPSS. It's the same definition coefficient of determination.
It's the same.
R squared.
Is R squared, yeah. That's the same.
The
They
same.
call them different terms, yeah. They're the same. And everyone does R squared because everyone is taught the same way. And it's simple. You can do R squared in Excel like nothing.
Yeah.
Okay, it calculates it for you. So everyone does this. And it can work. I mean, I can have, okay, something that lines here that, you know, you have this, and it does the average in between, and you can still see that it's overall pretty good. There are times that it can definitely work, but I can also trick it. So my point is this: if anyone shows R squared, they should show it with a one-to-one line.
Yeah.
There's the difference.
Yeah.
You can use R squared all you want, but if I only show this, that means nothing. If I show it in relationship to that center line, now I can be determined, because now I know my data is underestimating.
Yeah.
So if you don't use the Nash-Sutcliffe, that's fine. You only use R squared, you have to at least show that middle line. Okay, so for example, let's take a good example here. Oh, these are, okay. So in this case, you can't use Nash-Sutcliffe. Does that make sense? Why? Because I'm not comparing the same value. So you have to use coefficient of determination.
Just function here.
Because it's a function. Because 500, you will never see 500 here. So you can't have that same. So you would use R squared. But when you're comparing the same value to each other, in which we do in calibration, same value to the same value, you should have a line that goes right through the middle.
So in the previous example, we have to use Nash, the other method.
No, and the one I just showed you, this one, you would use R squared. Because they're two different values, two different parameters that you're comparing. So they don't have the same value. Whereas when I showed this, I gave R squared, 0.93. And that is this black line. But I also gave this dashed line as that one-to-one line. This is why I did that, because these are the same parameter, so I made sure to have where the center is. And then I also said, from that you can see that the Nash-Sutcliffe is 0.91. So see, somebody might look at this and say, wow, your data's great, then they'd say, okay, it's a little worse than we thought. Still good, of course, but...
Yeah, nice.
So in modeling, And in statistical analysis of data of the two same type, you have to use another method. You don't have to use Nash-Sutcliffe. That's a popular one. You can do others, okay? But you can't use just that. And as Mahmoud has said, he's probably seen papers, famous people, and those famous people do it incorrectly. Okay? We're not saying that we're better than those famous people, but they're doing something that maybe they learned it this time originally and they haven't taken statistics. They haven't done something else. It happens. All of us will make mistakes, I assure you. Okay. So all of that equation says, and you can go through it, I didn't put what each parameter says, but if you type this in, you can see what each one means. But all that, again, puts it to a one-to-one line. That's the point of the equation. And you could simply type this into an Excel file and then get the values. Okay? And we know the R squared is even more simple, and that's the equation. And as I mentioned, sometimes people call it correlation coefficient, coefficient of determination. There's all different names for it. But they all say the same thing. It's just correlating two different data sets. But so these people that do statistics are mathematicians. They know math. If you ask them what granite is, they have no idea, right? But it's the same thing. Us, geologists, are attempting to use this without knowing it sometimes. So if you asked a mathematician every single time, they would say that this means I'm going to correlate two different data sets. That's what a mathematician would say. But somehow from math to geology, someone like myself one day said, oh, I can do this to compare two of the same data sets. I publish it, you see it, you publish it, you publish it, you publish it, and everybody's doing it wrong. That's the problem. Okay? But if you ask any mathematician, they will tell you this.
So when we deal with the same data sets, in which kind of representation we represent the same data sets?
If you have two of the same, like observed flow versus calculated, I would give the coefficient of determination, but in addition, you give the Nash-Sutcliffe or the one-to-one line, at least show where it is, or actually do the calculation for this as well. As an example, hey, how's it going?
Hello. Hi.
So now we're going to move to sensitivity analysis. Okay? So we said it measures the change in model output associated with the change, what we call perturbation, in model input. So we change the parameter. And we do it to select which parameters should be adjusted in calibration and which ones we can leave as default. So which one of these we can leave as what SWAT gave us, or which ones we have to change. To prioritize or make important that which data we need to collect. Right? So here, again, can I see this out? You know, you are missing 5 data points, or 5 data parameters. So you want to measure these in the field. Well, which ones should you do? You would run a sensitivity and it would tell us this is the most important one. I don't need to do the other ones. I would just collect data for this one. Make sense? And also to estimate potential errors. So maybe one of those parameters you find is sensitive. Right? You know it is. But there is no way that you can collect that data. Now you know the potential error then in the model. Okay, how do you know? Well, then let me give you an example. Let's say hydraulic conductivity. It became a very sensitive parameter, so you have to change it. You should. Well, you cannot. You cannot go out in the field, something happens, you don't have the money, whatever. Okay? So you'll say, okay, well, I know that this is sand. Sand has a range. It's from 50 to 150. So what I will do is I will run my model at 50. it will say my result is 10 millimeters of recharge. I will run my model at 150, and my result is 20 millimeters of recharge. So now when I know my error, I am an error of 100%. If I change my value, it will double my recharge. That's 100% error. Does this make sense, or should I write it?
Yeah.
Write it? Makes sense.
Makes sense.
أنت فاهم؟ Okay? And then I mentioned this uncertainty analysis. So I mentioned modelers have discovered that there's often more than one set of parameters that gives an adequate fit to the data. So we want to determine which is the correct fit. Which are the correct parameters? Which are the ones that we know the most or most comfortable with? So for example, an acceptable versus the parameters function, you can see that two of them are what we consider acceptable. Maybe this acceptable line is 0.8 correlation. And as a result, this gives 0.9 and this gives 0.85. So if you had two sets of parameters, one gave a 0.9 and 0.85, which one would you choose? 8.5 or 9?
You said that acceptable is about 4.8.
0.8 or better. So 1 is perfect, right? So if you have 1, you are a perfect match. So you would choose 1, right? So I'm saying this line is 0.8 because this is what most modelers assume is acceptable. So this gives you a correlation of 0.9 and 0.85. So which one's better? 0.9. Right? 0.9 is closer to 1. So this is why we do uncertainty analysis. Even though this looks okay, you would automatically choose this. The calibration would say 0.9, we're done, we're finished. This is the best correlation. But 0.9 might be on field data or non-field data. And 0.85 is based on field data. So we would look at the different parameters that caused it to be acceptable. And we would choose it based on which ones we felt were the most real, the most accurate. Make sense? I'll probably skip this a little bit, but I will tell you the method. I'm going to step back. I want you to write this down, because I don't have it on here. For sensitivity analysis, the method that SWOT uses is called, I'll give you the acronym or the letters first. It's L, H, hyphen, dash, OAT. OAT, yeah. LHOAT. This is the program or the function that SWOT uses to calculate sensitivity. And that stands for Latin. That's it. So just so you know, it stands for Latin hypercube 1 factor at a time. And what that means is they adjust 1 factor at a time. Has anyone heard of a Monte Carlo simulation?
Yeah.
Have you heard of Monte Carlo simulation?
Monte Carlo.
No? Yes?
Monte
Okay.
Carlo.
So Monte Carlo simulations mean that you adjust your data by holding one parameters, all of them the same, and you change one at a time and see what the results become. Call that a Monte Carlo simulation. And there are hundreds of types of those.
ANOVA.
Okay? But this one chooses one called the Latin hypercube 1 factor at a time. That's the method. Okay?
We can do it with abstract. This method of correlation.
Yeah, you'll do this in SWOT. This is an automatic thing in SWOT. So again, you don't have to know it. You would push a button that says run sensitivity analysis and it would give you the result.
It's automatic.
It's automatic. But we don't like automatic. We want to know what it's doing, right? We don't want a black box. We want to know, if we know what it's doing, we know what could be the problems. So I'm telling you the method that it chooses. So for uncertainty analysis, it uses a method called glue. And different models will choose different methods. And I mean generalized likelihood uncertainty estimation. So these are these mathematicians, these statistical people, these computer engineers. They get together. Actually, Bevan is a mathematician and Binley was a computer engineer. And they got together and they found out what's the best way that we can look and compare different data sets. So they take a simulation, they compare it to an observed value, and then they put basically a likelihood or a chance of success, and they put a weight for each value. So for examples, all the parameters of the blue dots, you can see are different parameters, parameter 1, parameter 2, or 2, 1. And they both give a value of 0.75. So then we would go back and say which set is correct, and we would do that based on which one are we most comfortable with.
Which one close to 1?
Well, not just close to 1, because close to 1 might be all non-field data. We might have guessed at those numbers, right? So we start with saying which is the closest to 1, but then when we have ones that are considered acceptable, then we look more closely at those ones. So here, this would be a value of 0.1. We don't even care. We won't even look at it. Make sense? Okay, so you'll see the steps. I will talk about them. But then again, you can think about this, process this on your own as you're at home and reading it, and then come back if you have questions. So the first step, we select a combination of parameter values at random and simulate the model for each combination. So if we wanted, when we run a calibration, okay, you will run this in SWOT. You would say run calibration. It's going to ask you which parameters do you want to run it on. And which parameters would I choose? As my question to you, which parameters would I tell my model to calibrate? Which ones?
Stream flow.
The most sensitive. So I would actually run sensitivity analysis first. The first thing I do. It would give me my 10 parameters. Then I would tell the model to do those 10. Okay? But before I give the model that, I would run an uncertainty analysis. I would give... No, sensitivity first. I need to know which ones are sensitive. Then I would run an uncertainty analysis. And I would use those 10. And some people then use more, but a lot of people will use the most sensitive ones. And tell it how many combinations will it give me. And it'll give me 5 or so. And I would say which one is the most accurate in terms of that I feel most comfortable with in the data, whether I collected it or I downloaded it or you gave it to me. I would assess this. And then I would run the calibration with those set. Does that make sense? So first I find out which ones are sensitive. Then there's 20 of them. And of those 20, I only collected 3. You know, I was lazy. I only collected 3. I would run the uncertainty, and whichever ones used my 3 as best as possible, I would choose that one. And then I would tell the model to calibrate and adjust those parameters last.
So from the three which we measure, we select one for uncertainty. One of the three for uncertainty analysis.
No, what you would tell the computer, the SWAT, to use all. It's going to ask you when you run an uncertainty. It will say which parameters do you want to choose.
I can choose the three.
You would choose. You could choose just 3, but usually you give them the set that are sensitive, the set of 20. Even though you didn't collect all of these, you would choose the set. Yeah, some people choose all of them. They'll choose all 1,000. Okay, but to me, it can take months to run, or you can have other problems. Sometimes if you choose all 1,000, it gives a bad result because it's too many of them. And so most people would pick this sensitive. They'll take 1,000. They'll run this, gives you this. They'll take those, put it into uncertainty. It will tell me 4 different sets work. I will choose which set is the most of my field data. Set 2. Okay? And then I would take set 2 and I would calibrate the model, which means I would adjust those set of parameters up and down to make this match that. Does that make sense?
Mm.
So in here we collect them either at random or simulate the model for each combination. We compare their R squared, and we simulate those at acceptable points, weight output to determine characteristics, like variance and other things. But this is the stuff that's done automatically. So the calibration, uncertainty with it. Okay. I think I'll just briefly say some limitations of this method. One is it assumes what we call an input sampling distribution, which means we have to give it a set of values. Sometimes it can require a very large number of simulations, which takes time, but that's it. Sometimes we get very good or very few good or acceptable solutions. So meaning a lot of times we just get things that are down here and only one up here. Okay, we hope that we have 10 up here, right? But most of the time we only get the ones down here. Okay? And in this case, it would require a very large number of simulations to produce any number that are acceptable. So what this means is, in order to produce that, sometimes we have to increase the number of parameters that we're looking at. So I said, ideally, we would take our most sensitive and run it, and it would give us multiple sets to choose from. But in reality, that doesn't necessarily happen. So we would have to go back and increase the number of parameters just to get something that is acceptable. Okay, but you'll see this through trial and error, through practice. As you practice, you'll say, I ran it and it gave me none. Then you'll add more to it. Okay? And then you hopefully have a calibrated model from which you can take and then do all these other ideas to it. Okay? So, does anyone have any questions on that lecture, or today anyways? Tomorrow we'll do the whole week stuff, but just on this stuff today. Any questions for today? No. Okay, so what we're going to do, I'll just put this up for the brightness. We are going to finish the soil. So how many people are finished with soil?